Hello everyone, welcome to the first video of what is hopefully going to be a series of videos where I talk about individual numbers and some interesting properties about them. And today what I'm going to be talking about is Graham's number. Now, there are other videos online that you can find about Graham's number, but all of them refer to a number that was different from the original number that was actually used in the mathematical proof. So I'm going to tell you about that first a little bit, and then I'll let you know the differences between them. But basically, Ron Graham and Bruce Lee Rothschild were working on a problem in Ramsey Theory that I'm going to explain in a minute, and they came up with an upper bound to the problem. But then Martin Gardner, another mathematician, saw the number and thought that it was a little difficult to explain to people, so he asked Ron Graham to come up with another number that was larger and then prove that one was also the upper bound. And that's the one that's most famously known as Graham's number, but I'm going to be talking about the original number that was actually used in the mathematical proof. It's a little more complicated, but it's still pretty simple, so I'm going to explain it for you guys. So what the problem is a problem where if you take 4 vertices of a square and you can color the lines either red or blue. Let's say you can color this red, including the diagonals, and color these blue. That's one way that you can color them. And basically what you're trying to do is you're trying to avoid a sort of configuration where they're all red or they're all blue. We want to avoid these. Obviously that's pretty easy to do, but the problem involves what happens if you go into higher dimensions. So let's say you have a cube, have 4 vertices here, and then 4 vertices in the square. Let's say you color, I don't know, some of these red, I don't know, it doesn't really matter, color these red, and color some of these blue. You know, it doesn't really matter exactly what vertices you're coloring which way, as long as you're trying to avoid this configuration. And what's important is that this configuration has to be on a flat plane. You can have them going out into 3 dimensions that have things like this, that's fine. You just want to avoid having all red or all blue on a flat plane. Now in 3 dimensions, you can avoid it pretty easily. In 4 dimensions, you can also avoid it. So if you can imagine a 4-dimensional hypercube, you can avoid it in 5 dimensions, 6 dimensions, and the question is, can you always avoid it? And the answer is no. And Graham's number is basically how many dimensions you need in order to guarantee that you cannot avoid it, no matter how you color the lines. Now, the actual value of Graham's number, because it's an upper bound, is actually likely much smaller. In fact, the upper bound has since been decreased by a fair bit. We know it's at least, I believe, 13, but it could be much, much larger. But when you get to Graham's number dimensions, you cannot avoid this. So now I'll tell you how big the number is. So what we need to do is introduce a new series of operations called Nuth arrow notation. So you have A arrow B, and you can have any number of arrows. Let's say you have C arrows. This is the function, or the operation. And the rules are, if you have a single arrow, A single arrow B, that's just the same as A to the power B. And if you have any more than one arrow, A C arrow B, that's the same as repeated operations of A of C minus 1 arrows of A, where you have B A's. This might seem a little confusing, so I'll give some examples. Turn the page, get a new page for this. Let's start with a single arrow. We got 2 arrow 3. This is the same as 2 to the power 3, which is 8. Then we have 2 double arrow 3, this is repeated over the single arrow, so that's 2 arrow 2 arrow 2, which is 2 to the 2 to the 2, which is 16. If you had something larger, like say 2 arrow 5, this would iterate 5 single arrows, which is 2 to the 2 to the 2 to the 2 to the 2. And when you're doing exponents or any sort of higher operations, you work right to left, top to bottom. So this would be 2 to the 2 to the 2 to the 4. 2 squared is 4. 2 to the 4 is 16, so that's 2 to the 2 to the 16. 2 to the 16 is 65,536. So that's 2 to the power 65,536, which is a pretty big number. Now let's go to triple arrow 3. And just like double arrows iterate over single arrows, triple arrows iterate over double arrows. So that's 2 double arrow 2 double arrow 2. We already saw that 2 double arrow 2, no we didn't. Wait, 2 double arrow 2 is just 2 single arrow 2, which is 4. So this is 2 double arrow 4, and in fact, any number of 2's between, any number of arrows between 2 2's will give you 4. So that's 2 double arrow 4, so that's 2 to the 2 to the 2 to the 2, which we already done this here, that's 65,536. Now let's do 2 4 arrow 3, and the quadruple arrows iterate over the triple arrows, so this is 2 triple arrow 2 triple arrow 2. 2 triple arrow 2 is 4, that's 2 triple arrow 4, which iterates over the double arrows, so that is 2 double arrow 2 double arrow 2 double arrow 2. And this 2 double arrow 2 is 4, that's 2 double arrow 2 double arrow 4. 2 double arrow 4 is 65,536. This is 2 double arrow 65,536, which iterates over single arrows. So this is a power tower of 2's 65,000 2's high, which is a very, very, very large number. Much, much larger than any number that you could fit in the entire universe. And that's only like 6 2's would be way too big for that. And then we have 65,000 of them. So the arrows make the numbers get big very, very quickly. Now let's do 2 5 arrow 3. This is 2 4 arrow 2 4 arrow 2, which is 2 4 arrow 4, which is 2 triple arrow 2 triple arrow 2 triple arrow 2. 2 triple arrow 2 is 4, so that's 2 triple arrow 2 triple arrow 4. 2 triple arrow 4 is the same as 2 quadruple arrow 3. We already saw that, so that's 2 triple arrow, this giant tower of 2's. And the triple arrows iterate over double arrows. So this is 2 double arrow, 2 double arrow, 2 double arrow, 2 dot 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 dot. Where the number of double arrows is the giant power tower of 2's. So what does this look like? Well, we start on the right with 2 double arrow 2. And then that tells you how many 2's are in the tower below that for the other double arrows. But that tells you how many 2's are in the tower below that. And that tells you how many 2's are in the tower below that. And you keep going. And the number of towers you have is 2 triple arrow 4, which is already this huge power tower. And essentially every new arrow you get will add a new level of iteration beyond exponentiation and power towers. So the numbers will get big pretty quickly. But we're still not even close to Graham's number. The first step in Graham's number, G1, is 2 12 arrow 3, which I can't really write out in terms of exponentiation because it would be 7 levels of iteration beyond what we've already seen. It's way too big. But then, G2, the next step, is a 2 arrow and a 3, but the number of arrows between the 2 and the 3 is G1, which is so big that now I can't even write down all the arrows and we've seen just how quickly adding a single arrow can make things go humongous. But now the number of arrows itself is this ridiculous number, so we have no hope of actually visualizing it ever. Then G3 is a 2 and a 3 with G2 arrows, and so on. You keep doing this. G4 has G3 arrows, and so on. And Graham's number is G7 with G6 arrows between the 2 and the 3. Now, this is the original number used in the proof by Graham and Rothschild, but it's not the number that is most commonly seen or identified as Graham's number online. That number is a little bigger, but I'm not going to go over that this time. If you want to find a video on that, you can look it up online. That'll tell you more about the classic Graham's number. But this is the actual number that was used in the original proof, and it's very large. And I don't think I've ever actually seen anyone talk about the original Graham's number, so I wanted to make this video. Thank you guys for watching. Have a good day. Bye.